In the first video of this deep learning series, we saw how a neuron applies some transformation to our data, and by doing it again and again, he was magically able to guess the output of the new data. Now we will logically see how it does it and go into some amount of depth. As far as you know, neurons take something as input and output the prediction, but something is going inside this neuron by which he can calculate this prediction. So to calculate it, the neuron is partitioned into two. The left side of it does the summation operation and the right side does the activation operation. We won't talk much about the activation function in this video as it is the topic of our next video. First of all, what is this string-like structure here? It is not just for fashion. They are weights of our neuron. The weights are the amount of strength by which inputs are connected with the neuron, and they are denoted as W1, W2, W3 as follows. But what do I mean by strength? Let's discuss that with a simple example. Suppose you want to predict the price of a car given three inputs. The first is a type of engine, then the name of buyer, and last is the price of fuel. So as the training proceeds, our neuron will come to know that the type of engine in the car influences the price too much. So the strength between the feature and neuron will be high. But in the case of buyer's name, the weight is very less because it's obvious that buyer's name does not affect the price of car at all. The last is the price of fuel, which our model has kept value intermediate between the above two because it indirectly affects the price of car, but not that much. After all, more the price of fuel, lesser the demand for cars and less will be the price of cars. Something like that. That's why weights are essential to tell the importance of input. Now we will talk about this summation operation. The summation operation takes every input value and multiplies them with their consecutive weights and adds all of them, and the output we get after doing this is known as the weighted sum. Usually we deal with the inputs and weights in the form of matrix. The input matrix is the matrix we give for training, and every column in this matrix is a feature. In the previous example, type of engine, buyer's name, and fuel price are features. Now if there are three columns in the input matrix, the weight matrix will contain three rows, and each of the values is the strength between that input column and neuron. Like for the first column, the strength between that and the neuron is 1.4, which is the first row of our weight matrix, and the same goes for all. Now we can do the summation operation. For that, we will multiply every column of the input matrix with every row of weight matrix and sum all of them, and the answer we get will be our weighted sum as discussed previously. That's why to generalize the formula of weighted sum, it can also be written like this. But if you even know a little linear algebra, you can guess that this formula is of dot product. In the algebraic definition of the dot product in Wikipedia, you can see that it is exactly equal to our previous equation. So we can modify it and write it in the dot product form. This dot here is the dot product between the input matrix and weight matrix. One thing which I have not introduced till now is the term bias. Bias is the single value that is added to the summation operation or the weighted sum. With bias, we can shift our weighted sum equation to either left or right. The best way to understand this is via visualization. Let's take an example of a simple classification problem that you have to separate the blue points and the orange points. You have to bring this line a little down. We can do that by altering the slope of this line. Slope is nothing but the steepness of the line, which is a synonym for weights in mathematics. Currently the slope is 2, but to separate these points we have to bring this line a little to the down. So let's change that 2 with 1.2. Yes, now we have separated the points. But what if these points are like this? Now we cannot separate these points easily. This is where bias comes to the rescue. By bias, you can shift this line either upwards or downwards. Bias is the points where our line intersects the y-axis. Now our line is intersecting the y-axis is at 2. That's why the value of bias is also 2. And now we can alter the slope of this line and we have separated the data. The real world data are even complex than this. So without bias, our neuron can never fit the data well. In short, this is the final thing that is happening inside the neuron to calculate the weighted sum, and this weighted sum is nothing but the y-pred. You can also see the formula in the Tensorflow documentation of the dense layer. The entire diagram you are seeing now is known as the perceptron algorithm. It was invented by Frank Rosenblatt in 1958 and is also considered as the father of deep learning. Now enough of the theory stuff and let's dig into some code part of what we have learned till now. First, we will import Tensorflow to create a neuron and NumPy to create a fake data. I have just arranged number from 0 to 23 in 3 columns and 8 rows. And the matrix we have got now is our input matrix. Now let's create a neuron that is quite simple with TensorFlow. We will write tf.keras.layers.dense, which is a class, and the first parameter it accepts is the number of neurons we want. In our case, we only want one neuron, so I have just written 1 here. Now we can calculate the output by passing our input matrix, but before viewing the output, let us see how our weight matrix and bias looks like. We can easily get weights by typing neuron.kernel and bias by neuron.bias. I am writing this .numpy to convert our matrix from tensor format to numpy format. Now let's see the weights. It has 1 row and 3 columns as we discussed previously, and bias contains only 1 row with a value of 0. As of now, these weights and biases are completely useless because they are randomly initialized. But when we actually train our model, these two variables change with every epoch to make the accuracy higher. Just let it go. If this thing is not making sense now, it will completely become clear in some future videos. Now let's see the output, and this is our weighted sum matrix or the ypred. But we have deduced the equation of ypred earlier, which is the dot product between input matrix and weights plus the bias. So by this knowledge we can even calculate output on our own. Let's do that. I have used NumPy to do dot product between input matrix and weights and simply added the bias to it. And if we see our output now, it is completely equal to TensorFlow's. If you have understood everything up to this point, then yes, you almost know everything that is happening in the neuron to calculate the ypred. But we haven't discussed the right side of this neuron, which is the activation operation. Though we have come along the word activation 2 times in this video only. So in the next video, we will discuss about activation functions, which is an extremely important topic. Until then, see my other videos, and if you are from very future, I may have already uploaded many videos in this series. So you can get the playlist link in the description and many other useful resources. See you in the next video.